Okay, these are some problems from section 9.4. I might go a little bit fast, so you may have to pause it to check this out. It is too fast. Number 1, if you looked at it, it was negative 1 over x plus 4, and the series was a geometric series generated by this. So we could take a look at this, and I just kind of showed the manipulation to get it to be 1 over 1 minus x plus 5. We just put the minus sign down here, and then kind of made this negative 5 is negative 4, so it's the same thing. Then I factored this out. So you can see it's 1 over 1 minus r, so to speak, and that was my ratio when you looked at the power series they had written in number 1. So we want to find the values for which the equation is an identity. So we just want to find out where it converges. What converges is a geometric convergent series, so x plus 5, that was the ratio, equals r. It converges when x plus 5 is less than 1. So when the absolute value of r is less than 1, so the absolute value of x plus 5 is less than 1. So we can just rewrite this as x plus 5 is between negative 1 and positive 1, and then just subtract 5 from both sides, so that becomes negative 4 and negative 6. So there's your interval which it converges. On number 2, same idea. This is a little bit even more straightforward. 1 over 1 minus x, so this is a geometric series. X equals r, converges when the absolute value of r is less than 1, so when the absolute value of x is less than 1, so x is between negative 1 and 1. So that wasn't too bad either. Okay, that was number 2. Okay, and then number 3, use a comparison test to show that the series converges for all x. So remember, e to the x, this does converge for all numbers, and that's a summation n equals 0 to infinity of x to the n over n factorial. And this was the series that we want to show converges by comparison. So I just looked at the argument part of the summation, and I know that this is going to be x to the 3n over 2n factorial plus 1 was going to be less than or equal to x to the 3n over n factorial. Okay, because this is going to make the bottom bigger, which will make this makes the bottom larger. So if I subtract that, it's going to make the bottom. Well, if I subtract this, it's going to make the bottom smaller, which will make the fraction larger. And then since n is going to be positive, if I just take the 2 out, it's still going to make the bottom smaller, because this is smaller than that for n greater than 1, or n is 1 and greater. So if I take this out, this is also going to make the bottom smaller, which will make the fraction larger. So this is going to be larger than this. Okay? In other words, if you make the bottom smaller, you make the fraction larger. So if I take a 1 away, it's smaller. If I take the 2 factor, it becomes smaller, makes that larger. So this is less than x to the 3n over n factorial, and then this is easy to show that this can be written as a form of e. Okay, so x cubed from this, x cubed to the n over n factorial, and the summation from n equals 0 to n infinity of x cubed to the n over n factorial is the Taylor series for e to the x to the third, which converges for all x. So since this converges, by comparison, this must converge because this is smaller than that for all the terms. So it's kind of forced down into it. Okay, and then number 4. Here's number 4. And it's the same idea. X to the 2n over n factorial. This was the series here. Again, we want to show that converges by comparison. Well, this is going to be smaller than this because, again, I'm going to make the denominator smaller, which will make the fraction larger. And then I can rewrite this like this, and then this again is going to be just a form of e to the x squared. So that's going to be the Taylor series for e to the x squared, which converges for all x. So that's kind of the technique you use on those. Okay, let's take a look at number 5. And number 5, we want to show that the series converges absolutely. So this was a series right here. This is number 5. So this was the series. So I just take the absolute value of the argument here of the series, this part, and I want to show that converges. And if that converges, the series converges absolutely, which means the series converges. So this is easy to break up. This is always going to be positive, so I don't need the absolute value for that. And again, if I make the denominator smaller, it's going to make the fraction larger, so this will be less than this. Okay? Well, we know that the absolute value of the cosine, any power, the cosine is less than 1, it's between negative 1 and 1. So if I square that, it's still going to be between negative 1 and 1, so it's going to be smaller than 1, so I can replace this by 1, and 1 over n factorial. So this is going to be less than, so by 1 over n factorial. So the absolute value of this, by comparison, converges to E. Because it's less than this, which converges to E, so by comparison, converges. All right? Because it's, by the comparison test, it is smaller than a convergent series. I should say converges to E, but it converges. All right? So since this converges to E, it converges. Remember, this was our form for E, and then if we put 1 in, actually E equals 1 over n factorial, it converges to that value. Okay? And then number 6, the same idea. 2 sine x to the n factorial plus 3. So we want to show that that converges absolutely. So we're going to do it by comparison also. Well, first of all, we take the absolute value. And again, I can make the denominator smaller, which will make the fraction larger. So this will be larger than this. Oops, forgot my absolute value, pardon me. Should have an absolute value here. And by the same respect, this will be less than 1. And so I can take the 2 out, so this will be less than 2. Because the absolute value of that is going to be less than 1. So this will be less than 2 over that. And then again, since 1 over n factorial converges to E, this converges to 2E, which is a real number. So since this converges, and by comparison, the absolute value converges, so it converges absolutely. All right, and then number 7. Through 22, we want to find the radius of convergence of the power series. Well, if I look at number 7, this is just a geometric series. So the geometric series converges. Remember, the radius, the ratio is x. All right, because it's just 1 times x times x times x. I keep getting the next term. So the r is equal to x, so converges for the absolute value of r is less than 1. So converges for the absolute value of x is less than 1. So the radius of convergence is 1. Okay. And then number 8. Same idea. We have another geometric series. The summation n equals 0 to infinity of x plus 5 to the n, so 1 plus x plus 5 plus x plus 5 squared. It is also a geometric series. R is equal to x plus 5, so it converges for this absolute value of x plus 5 is less than 1. And this is in the form x minus a, so that's, if we look at the theory of a convergence, we talked about this, that's going to be in the form x minus a. So this is okay. So this still is less than 1, so the radius of convergence is also 1. Okay? So that's 1 through 8. Hope that helps.